So now that we've discussed molecular geometry, we can start to talk about the concept of polarity. So bonds can be either polar or nonpolar. Molecules can also be either polar or nonpolar. And this distinction has a huge impact on both the physical and chemical properties of a substance. So it's really, really important. And we'll get more into that impact next week. But for today, we're just going to be looking at how we determine whether a substance or whether a molecule is a polar molecule or a nonpolar molecule. So the first thing we have to determine is whether the bonds in that molecule are polar or nonpolar. So a nonpolar bond is one in which electrons are shared equally between the bonded atoms. This occurs when our atoms that are bonded together have the same or very similar electronegativity. Remember that electronegativity was the tendency of an atom to attract electrons towards itself. So it's essentially how hard is it pulling on the electrons in the bond. So when our two atoms are pulling by pretty much the same strength, our electrons end up being equally shared between the two atoms. So this occurs when the bond is between two atoms of the same element. So something like an iodine to iodine bond, a hydrogen to hydrogen bond, any two atoms of the same element directly connected, or carbon-hydrogen bonds are also considered nonpolar because their electronegativities are quite similar. A polar bond is one in which electrons are not shared equally between the bonded atoms, meaning that the electrons spend more time near one atom than the other. And this occurs when our atoms have significantly different electronegativity. Essentially, one atom is pulling on the electrons a lot harder than the other. So you can kind of think of it like a tug of war. The one that pulls harder is tugging the electrons towards itself, and they spend more time over on that side. So bonds between atoms of two different elements, except for carbon-hydrogen, are generally considered polar. The bigger the difference in the electronegativities, the more polar they are. So because of this uneven distribution of electrons, polar bonds have an uneven distribution of charge. The element with the higher electronegativity will have a slight negative charge. We indicate this idea of a slight negative using a lowercase Greek letter delta, which looks like this, and a negative sign, just meaning that it has a little bit of negative. It's not a full-on extra electron. It's not a full -1 charge like an ion, but it has a little bit of extra electron density around it because that one element with the higher electronegativity attracts the electrons more strongly. This leaves the element with the lower electronegativity with an electron deficit, which gives it a slight positive charge. So we often indicate that with a delta plus. So you'll see sometimes polar bonds, if you're looking to indicate the polarity, this is not like a standard part of the structure or anything, but if you're discussing polarity in particular, you'll often see either delta minus, delta plus drawn at the ends of a bonds to indicate where the positive and negative charges lie. So this is essentially telling you that this is the more electronegative element here. We know that fluorine is the most electronegative of all, so that makes sense. Another symbol that's pretty common is the use of the arrow with a little cross at the back. So the little cross is meant to look like a plus sign, which goes at the positively charged end. So these two symbols are both used interchangeably, the delta plus, delta minus symbol or that arrow. You don't usually see both of them on the same structure the way I've done it here, but you certainly could if you wanted to. They just mean the same thing. So molecules can also be polar or nonpolar. So a polar molecule, also known as a dipole, have an unequal distribution of electrons on different sides. So essentially there's an imbalance of charge in the molecule as a whole. In order for a molecule to be polar, Firstly, it must contain polar bonds. If it does not contain polar bonds, nothing else matters. It can't possibly be polar. And those polar bonds must be somehow asymmetrically arranged around the central atom, which means we need to consider the molecular geometry. So if we look at our molecular geometries chart from the other day, so everything I'm talking about in these examples is assuming that all of our bonds are equally polar. So, looking at the first geometry here, the linear geometry, if these two bonds are both equally polar, they point in exactly opposite directions. As it's drawn here, one points straight to the left, one points straight to the right. Essentially, these cancel each other out. So this is a symmetric arrangement, which means that even if these bonds are polar, the molecule as a whole is nonpolar. Assuming our two bonds are the same, the molecule is symmetric, and therefore this would typically be a nonpolar arrangement. Similarly for trigonal planar, this one's a little bit less obvious, but we have one that points straight up, one that points down and left, one that points down and right. So the up from this one kind of cancels out with the down from these two, and the left of this cancels the right of that. So again, all of these are equally distributed around our central atom. So this would be a symmetric arrangement. If all of our bonds are the same, this would be nonpolar. If you've worked with vectors at all in math class, if your vectors add to 0, it's nonpolar. If they don't, it's polar. If that didn't make sense to you, that's fine. Don't worry about it. Looking at our bent geometry, we see we have these two bonds and a lone pair. So we're not really considering our lone pair. It's just the arrangement of polar bonds that needs to be asymmetric. And we can see that we have down and left, we have down and right, but we have nothing that points up. So overall, we have a net dipole that points in this direction. So polar molecules are known as dipoles. The dipole moment is a measurement of polarity. It's a measurement of exactly how polar something is. Which depends both on how polar the bonds are. The bigger the difference in electronegativity between your two atoms, the more polar your bonds will be. And it can depend on the arrangement as well. So in this geometry here, the left and right aspects cancel out. So part of these bonds, part of the directionality of these bonds is canceling each other out, but we're left with just this little bit of a down. So we do have a non-zero dipole moment here, which is what this pink arrow is representing. So this is an asymmetric arrangement that will often lead to a polar molecule, as long as the bonds are polar. So we can think of a similar analysis for all of these. In this one, again, we're getting into 3 dimensions now, so this gets even harder to visualize. But these bonds are distributed equally all the way around our central atom. All of our bond angles are the same, all of our positions are equivalent. So this would be a symmetric arrangement. This one, all of our bonds kind of point down and nothing points up. So we have a little net overall dipole pointing somewhat down here. So this one is an asymmetric arrangement. Trigonal Bi-Pyramidal, we have one pointing straight up, one pointing straight down. Those cancel each other out. And then these three point to the corners of a triangle, equally distributed around the central atom in that plane. So this one is symmetric as well. For seesaw, we've got straight up and straight down are going to cancel each other out. But then we've got these two that both kind of point to the left with nothing pointing to the right. So our overall net dipole here would point a little bit to the left. Moving on over. The angle of this one's weird, but we have this bent geometry. These bonds are drawn both kind of pointing towards the back, which is a little bit difficult to draw, but we have a slight dipole going in that backwards direction, since there are no bonds pointing towards the front. This one is asymmetric. T-shape, straight up and straight down pretty much cancel each other out, but we've got this one pointing to the right with nothing pointing to the left. So that is also pretty much our net dipole here as well. Then we're back to a linear geometry with our bonds pointing in exactly opposite directions. So this one is symmetrical. And then in our last row, we have for octahedral, bonds pointing up and down will cancel each other out. Left and right will cancel each other out. Front and back will cancel each other out. So that one is symmetrical, is nicely balanced. Our square pyramid, we have bonds to the front and back, which will cancel each other out. Left and right will cancel, but this one pointing straight up, there's nothing pointing down. So our overall dipole is going to point in that direction. Square planar, we have front and back, cancel, left and right, cancel. So this one is symmetric. T-shape, front and back, cancel, but this one to the left does not have anything to the right to balance it out. And then last but not least, another linear. These guys point in exactly opposite directions. So that is a symmetric arrangement. So what you'll notice about our geometries is that the ones that are asymmetric, the ones that are most commonly polar, are the ones that have a lopsided arrangement of lone pairs, that it's really lone pairs that create this asymmetry in our molecule, that this one lone pair here is kind of pushing these two bonds down, which makes that bent shape. Same here, these two lone pairs push those two bonds in the same direction, giving us that bent shape. So again, all of these sort of thought processes that we just went through are assuming that all of the bonds are equally polar, which is not necessarily always the case. So let's look at a couple examples of how we figure out whether something is polar or not. So the first thing we're going to want to do is to draw the Lewis structures and figure out the molecular geometry, since we're going to need to consider the shape. So why don't you pause here and take a minute to do that much. Draw the structure and figure out the molecular geometry. So our first structure is going to be water. Oxygen will be our central atom with hydrogens around it and two lone pairs. SF4 will have sulfur in the middle, 4 fluorine atoms around it, filled in with lone pairs, and then there's one extra pair of electrons that will need to go on the sulfur. CO2, we'll have carbon as the central atom with oxygens on both sides. If we fill up the valence shells of our peripheral atoms, we would now be out of electrons, so we will need to create double bonds in order to fill the valence shell of carbon. So if we create two double bonds, we get the structure for carbon dioxide. And our last structure here for CH3Cl, carbon is going to be our central atom since it is less electronegative than chlorine. So carbon goes in the middle with chlorine and 3 hydrogens around it. So these are the Lewis structures for our 4 examples. So next we'll want to figure out our molecular geometries for these. So water has 2 bonds and 2 lone pairs, so that is 4 total electron domains, with 2 lone pairs makes it the bent geometry. So the molecular geometry of water is bent, which means that it actually looks more like this. So making sure that you're thinking about the actual shape is really going to help you determine polarity. So whether you actually draw it in the right shape or just kind of envision it on this picture that like, okay, this structure here represents water now. I can think about what that's going to look like. So in determining if water is polar or nonpolar, first we need to figure out if the bonds are polar. The bonds are between oxygen and hydrogen, 2 different elements, not carbon-hydrogen. So our bonds are polar. And oxygen is more electronegative than hydrogen. Hydrogen's kind of off on its own, I know, so it's a little bit hard to fit into this trend that we've discussed. But generally speaking, things that are considered highly electronegative are these guys. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine are generally considered high electronegativity. So other things are going to be lower than that. So you'll frequently find other things bonded to those. So hydrogen is not considered high electronegativity. Oxygen is. So oxygen is higher, meaning that it's pulling electrons towards itself. So each of our bonds is pulling electrons towards the oxygen. So we have this bond pointing kind of up and left here, up and right here. So the left and the right aspects cancel each other out, but there's nothing to cancel out the up. So the overall dipole points, in the way I've oriented the molecule here, straight up towards the oxygen. Essentially what this means is that this side of the molecule has a slight negative charge, and this side of the molecule has a slight positive charge. So this is a polar molecule because of that. This is really what we're looking for in a polar molecule, is that opposite sides have opposite charges. The top is negative, the bottom is positive, is what it really means for something to be a dipole, that it has 2 oppositely charged poles at opposite ends. So if we do the same thing for SF4, SF4 has 1, 2, 3, 4 bonds plus 1 lone pair, gives us 5 electron domains overall. So 5 electron domains with 1 lone pair is the seesaw geometry, which actually looks more like this. So our bonds are once again polar. Two different elements, not carbon, hydrogen. And we know that fluorine is the most electronegative element of all. So fluorine is going to be pulling electrons towards itself through each of these 4 bonds. So in the seesaw geometry, we have these bonds that point straight up and straight down, and we have these 2 that kind of point off to the right, with nothing pointing to the left to balance them out. So our overall dipole is going to point in that direction. So that means that this is a polar molecule, and that essentially this side, where the fluorines are, has a little bit of negative. The side where the sulfur is has a little bit of positive. So this is a polar molecule as well. For CO2, we have 2 electron domains. Remember that a double bond still only counts as 1. 2 electron domains is the linear geometry. So this one's actually drawn in pretty much the correct, not pretty much, in the correct shape. I'm going to draw it again just to be able to label things more clearly. So carbon-oxygen bonds are polar. So we have a polar bond going this way. Oxygen is more electronegative than carbon. It is closer to fluorine, so that is easy to see by the trend. So the oxygen atoms are pulling electrons towards themselves in both cases, but because they point in exactly opposite directions, these 2 bonds essentially cancel one another out. We would have a little bit of negative, that was really ugly, let's try again. A little bit of negative charge over here. Also a little bit of negative charge over here. We have the same charge on opposite ends, means this is non-polar. We're looking for opposite charges on opposite sides, which is not what we see here. We have some positive in the middle, but that doesn't really matter. So when we have this type of symmetric geometry, where everything about our molecule is symmetrical left to right, those polar bonds cancel one another out, and we end up with a nonpolar molecule. So our last example is CH3Cl. So this carbon has 4 bonds around it, which is 4 electron domains. None of them are lone pairs. So the geometry of this is tetrahedral. So it actually looks a little more like this. So in this one, we need to think about, are our bonds polar? We said that carbon-hydrogen bonds were not. So the only polar bond that we have is this carbon-chlorine bond here. The polarity depends upon the arrangement of the polar bonds specifically, and only the polar bonds. So this is where people get a little bit confused going back to this chart, where I said that tetrahedral was a symmetric arrangement. It is a symmetric arrangement if all of your bonds are equally polar, which is not the case in this last example. This bond is polar, the rest of them are not. So our only polar bond is pointing straight up here. There's nothing else to cancel that out because the other bonds are not polar. So our net dipole is exactly the same as that one bond because it's the only polar bond in the molecule. So we'll essentially have a little bit of negative charge on the top, and it's getting pulled away from that carbon, and the bottom of the molecule ends up a little bit positively charged. So this one is a polar molecule.